let's start. Okay, so good afternoon, everybody. So let's start. So last time I explained different applications for op-amp. I started with the first application here, inverting amplifier, and this is how you should connect the circuit. You need the feedback this way from the output to the input this way. Okay, this input, the non-inverting input, you connect it to ground, you put here R1 and the input here this way. And for this circuit, you need to memorize these circuits. I will tell you why. So here in this case, V output divided by V input, okay, is the gain. This is the gain. So here V output equal negative RF divided by R1 multiplied by V input. Okay. So it depends on how much amplification do you need. So if I can make, if this gain is 10, so actually V output equal 10 times V input. You amplify the input. Okay. So I can control the amount of the gain from this ratio, the ratio of these two resistors. Also, last time I explained what this negative means. Okay, negative. One more thing I wanna tell you here is I'm gonna do here very small trick. Look what I did here. It's these two circuits are almost the same, except I just flipped the source. You see what I did? I flipped the source. So actually here, this one here is actually V input, but here the input is actually negative V input. Makes sense? Because I just flipped it. So here is 0, this one becomes negative V input. Because of that, I will use exactly same formula, but in this case, V output should equal positive RF divided by R1 V input. Okay? So this one similar to this one, but they're almost the same, but this one here negative, this one is positive. Okay. So here is the output and the input are in phase. We call it in phase, but here out of phase. Okay. One more thing, it's the same circuit, but I'm gonna modify it a little bit. It's the same circuit, and then by modifying it, I'm gonna make a circuit. We call it summer or adding circuit. So the circuits that can add, you can do addition using this circuit. You will see how I made it. So it's exactly same circuit like this one. All what I did is I'm gonna add one more input here, resistance, and one more input. By this way, the output is going to be function in the summation of the two inputs. Okay, the output equals something multiplied by the summation of the two inputs. If you need, you can add more. So here I will show you an example for two. If you want to add two inputs, but you can extend the circuit to add more if you want. Okay. So here in this case, as you see here, this circuit is almost the same. As you see here, it's almost the same. Like this circuit, all what I did, I just added this branch here. Okay, everything else is the same. And okay, one more thing, you can add more if you want. I will calculate. I'm gonna calculate the output right now to you. You will see that the output should equal summation V1 plus V2. Okay, some function in the summation. So this circuit is used if you have two sources and you want to add them together. Okay, so let's do the math here. So I will. Let's get the final formula here. So I'm gonna use the same approach I used it before. So here, negative. Here we have positive. Here ground. Here we have R1, and here we have positive, negative V1, and then I'm gonna add one more here for R2, positive, negative, and here we have V1 and V2. Two sources here, okay? And then here we have RF. Okay. So again, I'm gonna explain it for two input, but still it's gonna be, you can get the same formula if it is more than two. So this circuit is used if you wanna add inputs together, okay? Let's see how we're gonna get the final formula. As you know, this is ground, so this one should be 0 volt as well, okay? Two things we use it all the time. V1 is equal to V2, so these two voltages are equal. Also, you know, the current here and the current here are zeros. So we use them all the time. Okay. Anyway, so that means we have here current I1, we have here current coming from here I2, okay, and then we have here current, I'm gonna call it IF. So if you apply Kirchhoff current law, so you have here I1 plus I2 should equal 0 plus IF. Okay? And I1 is actually V1 minus 0 divided by R1. I2 is actually V2 divided by R2, minus 0 for sure. IF is actually 0 minus RF, 0, sorry, minus V out divided by RF. Okay, so I'm gonna multiply by RF, multiply by negative. So I'm gonna just do some algebra manipulation. So V output should equal to negative, okay, RF divided by R1 V1 plus RF divided by R2 V2. So if I select R1 equal to R2, I'm going to select it equal to R. So in this case, V out should equal negative RF divided by R multiplied by V1 plus V2. So now I can do addition. And this addition, it's multiplied by a certain value. Okay, you can select RF divided by R equal to 1 if you want. And in this case, V out should equal negative V1 plus V2. Okay. And again, if you want to get rid of this negative, all what you can do, I can connect here, like you can switch it. So here in this case, so this one here becomes negative V1, this one negative V2. Okay. So again, you can get the same result if you add more. So when you go home, you can try to add more. So you can get the same equations, the same results. Here, R1 divided by R1 V1 plus RF divided by R2 V2 plus RF divided by R3 V3 and so on. So you can extend all these equations here. Okay. Here, this one, if R1 equal to R2 equal to R3 equal to R, so in this case, you have here V1 plus V2 plus V3 and so on. So this circuit we call it other, or we call it summer, because you can sum up or you add voltage sources together. Any questions? Okay. One of the things I did last time, so now you can use op-amp as inverting amplifier. This way, you can use it as a summer or adding circuit. Also, you can use it as non-inverting amplifier, as I explained last time. So non-inverting amplifier. In this case, it should be connected this way. So again, just to make it easy for you to remember, to memorize these circuits, you can see here, this circuit, if you compare this circuit to this circuit, it's the same. All what I did, all the changes I did here is, I just switched the ground and the VI. So here, VI was here, so I'm gonna move it to here, ground, I'm gonna move it here. So it's almost the same circuit. Okay. I want to tell you something. Please don't be confused. In the slide, sometimes I flip this op-amp, so I put positive up, negative down. So it should be the same thing. I just redraw the circuit. It's the same connection, the same circuit. Okay. Similar to what I'm teaching here. So anyway, so in this case, last time I explained, and even I was able to calculate, or I calculated the formula V out divided by Vn equal to 1 plus Rf divided by R1. Or V out equals to 1 plus Rf divided by R1 times V input. And you can tell why we call this one non-inverting. Okay, we call it non-inverting because this one is positive. Any questions? Also, I'm gonna do a little bit modification for this one, and then I'm gonna make a circuit. We call it voltage follower. I told you it's very important. Voltage follower. The way we are gonna do it is it's this way, negative and positive. So here I'm gonna make this one short circuit. So here this one I'm gonna make it short circuit, and this one open circuit. And now here we have V input and V out. This one is called voltage follower. And so in this circuit actually V out equal to V input. So that's why you can tell from the English name full, because the output voltage is following the input voltage. Okay. Also, I input is very close to 0. So it's not gonna take. So if you connect it between two circuits, it's not going to take much current from this circuit, very little current, almost 0. But here, I out here can be high current, okay? And that's because we don't do magic, huh? So because this current actually is coming from the bias we have here. I don't put the bias here in the figure, but you should know this current here, how you have an element that takes very little current and then it's going to give you high current. How you can do that? Okay, it's not magic, because this current actually is coming from the bias here. So we have a source here for the bias. It's not an input, it's just DC voltage. It should come from here. Okay, so V output equal to V input. I input is very small, I output is high. Okay, and also I told you last time why this voltage follower is very important. I'm sure 100% you will use it in your capstone. I'm sure because we use it all the time. Number one, I can use it to solve a problem if you have here a source, non-ideal source. For example, you have here RS, so this is non-ideal source. Okay, and then when I connect here RL, so, and here, for example, 5 volt, any numbers, for example, 5 volt. So I have a battery, this battery 5 volt, but what I'm gonna get here is not 5 volt. I'm not gonna get 5 volt, okay? What I'm gonna get here is actually, when you connect it, is actually, so here VL equal 5 volt voltage divider times RL divided by RL plus RS. So I'm gonna get a ratio of the 5 volt. Okay. How can you solve this problem? Very simple. All what you have to do is I can just connect. I can connect the voltage follower here. Okay. And even we did something interesting here. If you remember, the current I'm going to take from this source almost 0, very small current. Okay, but the RL is going to consume some power. So how you have a source and you are not gonna, this source does not generate any power and RL is still consuming power. How this happens? Okay, this is simply because the power consumed by RL are coming from the bias. It's not coming from the input here. So this is one way to use it. The other way, as I told you last time, and this usually what you need to do in your capstone. If you have a circuit this way, and the output of this circuit, I'm gonna call it, for example, V out 1, for example, and then I wanna connect this circuit to another circuit. I give you one example last time. For example, if you have microprocessor or microcontroller and you want to connect it to like a motor, for example, here. Okay, this problem we call it loading. Loading means this circuit number 2 is gonna load on circuit number 1. Okay, so loading here means because this circuit has our input here, input here. So actually, after I connect, the voltage I'm gonna have here is not the original voltage. but it's gonna be smaller voltage because you added a resistance to this circuit. So because if I just connect directly here, okay, what's gonna happen is the voltage I'm gonna get here is gonna be different or smaller than the original voltage of this circuit. So if this circuit, if there is no, if you don't connect the circuit to, you have a certain volt. If you connect it, you are gonna have a different voltage. Okay? This is one way to explain it. Another way to explain it is if you have a microprocessor, this microprocessor cannot give you more than, for example, 10 microampere, but I have a motor and this motor needs 200 milliampere, for example. So how I can connect them together? Okay, so in this case, I can put here the I can put voltage follower this one, okay? So that the input current here, the voltage will be the same. So here, the voltage here and the voltage here is going to be the same voltage, okay? But the current here is small current, the current here is big current, okay? Even last time, I explained there was one example I explained quickly at the end of the lecture. Yeah, so here I have a circuit this way, as you see here, we have a voltage source, we have two resistors this way, okay? This one circuit. So what is V out here? What is the voltage here? Okay, you can use voltage divider, which is V input times 60 divided by the summation, as you see here. So the result should be, or you can use Kirchhoff. Here I used Kirchhoff, but still you can use voltage divider 60 V input times 60 divided by the summation. So now the voltage here is actually 3 divided by 4 Vn. Okay. Now, so this is the voltage. This is the voltage without connecting this resistance. So you can see this resistance here, like another circuit. So now I want to connect another circuit here. So you can see here I'm going to apply Kirchhoff current law. I'm going to do the calculation. I see the voltage here dropped from 3/4 Vm to half Vm. Okay, because this is a loading problem. Okay, so in order to keep the same voltage, so that the output of this circuit equal to the input of the next circuit, okay, I can put voltage follower this one. Where this current is coming from? Coming from the bias, because I'm not going to take almost zero current taking. Any questions? So here I explain how the op-amp can be used to do summation. This is the addition I explained. Okay. Also, I explain how can we use it for amplification, inverting and non-inverting. How can we use it as voltage follower, and what problems this voltage follower can solve. Now, there is one more thing I'm going to explain is actually differential amplifier. Differential amplifier is the output should be the difference between the inputs. So this is like subtraction. I want to subtract the input. You got what I'm saying? So the output voltage is function in the difference of the input. So instead of addition, this one is subtraction. So let's see how I connected the circuit here. In this case, remember, in case of addition, the two sources are connected to the inverting input this way. Okay. So now, if I wanna do subtraction, so this one I have to move it to here to the positive. Okay. Yeah, as you see here. So one input here, as you see, the second input here to the positive this way, and this is this way. Okay. So after we do that, for sure I'm gonna do analysis right now. I will do the calculation, but just I want to show you after we do the calculation, after we do everything. Yeah, so you can see here the output here actually equal to R2 divided by R1. For sure, don't worry about the resistors. I can just make them one, right? So don't worry about this resistors. I can make this ratio one, or because sometimes I want to multiply the difference. Okay, so here, or I can make it 10, 20. If it is 10, so here the V output is 10 times the difference. This is the most important thing, is the difference. Okay, so this circuit subtractor, I'm going to subtract two inputs. and then I'm gonna multiply it by a ratio, which can be 1, can be 10, whatever you want, okay? So how you come up with this formula, I'm gonna tell you how. So again, I'm gonna use the same, I'm gonna do analysis here, similar to what we did before, okay? Number one, you know that V1 is equal to V2. V1 is equal to V2, okay? This is the first thing, this is the first thing I know here. One more thing here, I can apply Kirchhoff current law from node 1 here. When you apply Kirchhoff current law, so Vs1 minus V1 divided by R1, okay, which is this part here, should equal to 0 plus V1 minus V out, this way. You can also here you can apply Kirchhoff current law here, okay, as well. And if you do that here, you are gonna get a relation between V2 and Vs2. By the way, this is one way to do it, applying Kirchhoff current law. By the way, I can apply here voltage division, because there is no current coming this way. So I can simply say V2, or the voltage here, V2 is the voltage on this resistance R4, equals the input here, Vs2 times R4 divided by R3 plus R4. This is voltage division, okay? So I can apply it. By this way, I can get a relation between V2 and Vs2. Okay, here, this one gives me a relation V2 in terms of Vs2. I can take this one, okay, and then I can put it here because V1 is equal to V2. If I do that, I'm gonna have an equation that has only V input and V output. Again, if you look at this equation we have here, this equation has V1 and V out, okay? This V1 is equal to V2. This equation can give me V2 in terms of V2 in terms of Vs2, okay? So by this way, if V1 is equal to V2, so here I can get V2 from here, I can plug it in here. By this way, I can get a relation V1 and V1 here. So by this way, I can get a relation V output and Vs1 and Vs2. Okay, so if you do that, if you do the math here, this is the final equation you can get. Okay, V out equal to R2 divided by R1 times whatever. Okay, so here in this equation, I can for sure I can select some values for so this is the equation I got here, but I can select R1 equal to R3. So if I select R1 here is equal to R3. Okay, so this term, and also R2 equal to 4. So if I do that, 2 equal to 4. So this term can go with this term. Okay, and cancel each other. So if I can select R2 equal to R4, okay, and also R1 equal to R3, so this term cancels this term. So at the end, I'm going to end up with this one. Okay, so the V output here is actually gain, you put some gain here, times the difference, because here this one is differential. Differential means subtractor. I have a circuit that can do subtraction. Okay? Any questions? Okay. So let's have some examples here. If I wanna implement an equation like this one, okay, I need a circuit. This circuit Y here, this is the output of the circuit, is equal to negative times 10x1 plus 0.1 x2, where x1 and x2 are two inputs. Okay, so I have two inputs. I want to multiply the first input by 10. I want to multiply the second input by 0.1, add them together, and then multiply everything by negative. Okay. So if you look at this formula here, I want to do here. If you look at this formula, this is exactly the same formula I have for other adding other circuit or adding circuit. Okay. So as you see here, this is this circuit. So I can use this circuit here. Okay, because we have negative here, negative. So I don't need to do anything. We have x1 is actually Vs1, x2 is actually Vs2. So all what I have to do is I have to select the ratio of these two resistors to become 10. And I have to select the ratio of these two resistors to become 0.1. So I can use the same circuit here I have, but by selecting proper values for this resistor, I can make this one 10, I can make this one 0.1. That means this circuit can give me this relation if RF divided by R1 is 10. The first one here is 10 to become similar to this one. And RF divided by R2, 0.1. Is that okay? So I can select any values for this resistance so that this ratio is 10 and this ratio is 0.1. Is that okay? That's why this one, this problem has many solutions. It has unlimited solution. Okay? Based on, I can select any values for RF and then I get R1 and R2 from these equations here. Okay? So there is no one solution here. So here, RF divided by R1 equal to 10, RF divided by R2 equal to 0.1. I think the easy way you can start with RF. So I can here put R. You have two equations in 3 unknowns. But anyway, this is not the mean. If I'm not solving the equation, it's like I just want to keep this ratio 10. This ratio is 0.1. So I think the easy way you can just assume if RF equal to 10K, RF equal to 10K. If this one is 10K, okay. So here after that you can calculate R1 to becomes 1K, 1 kilo ohm. Same thing here. You can put RF 10K, and then you can find R2 with some value. So again, there is no one solution. There are many solutions here. But my advice to you, when you assume the values of the resistors, don't make these values very small, and don't make them too big, like open circuits and short circuits. You got what I'm saying? So don't try to avoid the range of ohms. Okay. Try to also avoid the range of mega ohms. Mega ohms is like open circuits, too much. You understand what I'm saying? Yes, you can select whatever you select here, but you need to be reasonable in the selection of these resistors. We have another example here. If I want to do something like this one, okay? This is addition. You are things together, but this is a negative here, okay? Yes, but this, as I told you, this is negative, so I can use the same circuit here for addition. So here I have X, one input here, X, but this one is negative, and this one is positive, okay? So still I can use other here, but all what I can do here, I can input negative Y instead of Y. Look here, or you can, so here you can flip this one as you will see. But there is one more thing you need to consider here. So again, I'm going to use the other circuit here, okay? But you need to keep in mind, if you want to use the other circuit, this is the formula we have. This is the formula. There should be negative here, okay? There should be negative here. And then I will see what values I should have for resistors to get 4 and 5 and whatever here, okay? So all what I'm going to do right now, I'm going to take negative outside here. I'm going to just do some very simple algebra manipulation so that I want to put this one in the format, in the general format of the other here. But after I add one more input here. Okay. So all what I did here, I didn't do anything. I just take negative outside. Why? Because this formula has negative outside. That's it. So I wanna make this equation in the same format of this one, and then I will decide what is the ratio of RF R1. That's it. Okay. So what I did here, I took negative outside. Okay. Once I negative outside here, so this one should be negative X. That means this input has to be negative X. Okay. How can you do that? Yeah, I told you it's very simple. Any input can be negative or positive. So if I make it this way, this positive and negative this way, so actually this one you input negative X. Here you input positive 1. Here I input negative 10. Okay. So let's see. So also here, this one, because this one already negative here, so now it is 5Y. So this input X has to be negative. That's why I flip it here, as you see here. This Y has to be positive. That's why I'm going to make it this way. Okay, very easy. You can control easily the input positive or negative. Okay? Finally, 2. How can you get 2? Yeah, again, I can get 2 by different ways because you need to multiply 2 things together. This is the general formula here. Okay. Yes, the final result is 2, but I need to multiply a ratio by a value, and that's what I did. I selected here 10 and 0.2. 10 times 0.2 equal to 2. Okay? So that I just want to put it in this format here. Can I select different numbers? The answer is yes. You can select any other numbers as long as the multiplication here is equal to 2. Okay? So here I just selected 10 and 0.2 just because I wanna make it in this format here. A ratio or some value here times another value. Okay, so I selected this one 10 and I selected this one 0.2. Okay, this one. And also there is a negative here. So again, I didn't do anything, I just rearranged it, or I did very simple algebra manipulation of this equation. This equation is equivalent to this one. Okay, but I changed it this way so that number one, I want to follow the format of this equation. Number one, there is a negative here. Number two, every term here, something multiplied by something else, something or by input, okay, or something multiplied by something else, okay, as you see here. So now, can you implement this one? Yes, now it's very easy. So here, as you will see here, but what about this? This one does not have an input. It has 10. So 10 can be a voltage source. Okay, so a voltage source with 10. Okay. So again, yeah, so here this is the equation I have right now. And this is the general equation. Okay. So now for this circuit, here, I'm gonna get this one. So now all what I have to do, I have to see what values I have to select for the resistors, so that this circuit gives me here 4, give me 5, give me 0.2. Okay, so that means RF divided by Rx should equal to 4, as you see here. RF divided by Ry should equal to 5. Okay, RF divided by R2 equal to 0.2. Okay, now I have 3 equations this way. I can select any value for the resistors as long as you achieve this one. My advice, because RF is common for all of them, you can start with RF, and then once you put some value for RF, you can calculate all of them. Okay? But again, you may select some value for RF, and you find some resistors are too small or too high, and now you can try another value. So try to be reasonable with the values you select. In grading and quizzes and exams, I'm not going to care about it. As long as the ratio is correct, it's okay. But practically, if you want to do it in practice, too small values is problematic. Too high values also problematic. Anyway, so here I just decided to select RF equal to 10K. Okay, and then here 10K divided by Rx equal to 4. I can calculate Rx. This one. 10K divided by R1 equal to 5. Now I can calculate R5. Sorry, R1. 10K divided by R2 equal to 0.2. Now I can calculate R2. Okay. This one has an unlimited number of solutions. Someone can select different values and come up with different values here. It's totally fine. As long as ratio here is 4, ratio is 5, ratio is 0.2, it's correct. Any questions? Okay. Okay. So here I just summarize what I have explained. This is the inverting op-amp circuit. You need to memorize this circuit as I told you, because maybe I didn't decide yet, but there will be a quiz, not next week, because already you are going to have a test next week. I have some mercy. So I'm merciful. I can give you a quiz and test. I will not do that. Okay, but I will give you a quiz after you come from the break. Okay, so anyway, so maybe I will give you a quiz after you come from the break. I can give you something like I didn't think about it yet, but I think that I can give you an equation like this one, and then I ask you to design it. So what I want to say is you need to memorize the circuits. Okay. For example, inverting has to be this way, and then non-inverting has to be this way. Follower has to be this way. Okay, so you need to memorize these circuits. Okay. The last example we have here, guys, is if I go to the beginning of this chapter, let me go to the beginning of this chapter. I told you in the very beginning, I have two models. I have two models for the OPM. One is practical model, okay, which is something like as you see here. So that means I have to this is a practical model. That means if you have an OPM in a circuit, I have to remove the OPM. I have to replace it with this circuit here and then do analysis. Okay, so here the OPM, the operation or the functionality of the OPM is equivalent to this circuit, like resistor, and then voltage source. Now, if your circuit has just a bunch of resistors and voltage source, okay, dependent voltage source, you can do the analysis because that's what we did in the previous chapters. From chapter 1 to 5, all what we have circuits with resistors and voltage sources. So now it should be easy. So all what you have to do, you have to complete the connection. So if you have a resistance here, so I have to connect the resistor here. Okay, so that's what I told you. And R here is a very high resistance between 10 to the power 5 or 10 to the power 12. This is input, very high resistance. We have a resistor here, which is a very small resistor. This gain here is too much gain, and the input here is actually the difference between these two. Okay. So this is the practical one. But we didn't use it. We didn't use it because it's gonna make the analysis of the circuit more complicated. And we use approximated one. We call it the ideal one. Okay. So in the ideal one, I assume here the current here is equal to that. We assume this Ri is infinity, open circuit. And because this one is infinity, it's not infinity, it's actually 10 to the power 12. Okay, which is too big. Anyway, so here this one is, we assume this one infinity, and because of that, this current is equal to 0, this current is equal to 0. And on all my analysis in this chapter, I assume the input currents are zeros. In reality, they are not zeros, but they are very close to zeros. Okay. So anyway, and because the current here is 0, these two voltages should be equal. Okay. So this is ideal model. That's what we use. So in the last example, I want to show you, although the ideal model is not the most accurate model, but actually it gives very good results compared to this one. Okay. In turn, I can make it less complex because if you use this one, it's gonna make the circuit too complex. Okay, and to gain very little accuracy. So I don't care much about it because still, even if there is error, it's a very, very small error. Okay? So I just want to convince you with that in the last example here. So in the last example here, we have a circuit similar to the circuits I explained in this chapter, and then I will ask you to analyze this circuit 2 times. One time using the ideal OPM, and the other one using the practical model or practical OPM. Okay, so let's start. We already analyzed this one. So we analyze this one. This is the inverting amplifier. Okay, so if you assume it is we analyze it using the ideal way. In the ideal way, I assume this current is 0. Okay, in the practical way, you will not. This current is not 0, but it's very close to 0. Okay. Here also we assume the V1 here is equal to V2. These two voltages are equal. If in the practical one, they are not equal, but as they are very close to each other. Okay, but anyway, so here we already did this one. This is the inverting amplifier. We already did it, and we found here the output. The output should equal negative. Again, we don't need to do the analysis again. We already did it. The output should equal negative RF divided by, we call it RF and RS. Okay, multiplied by Vs. Here we assume Rs is 1K, this resistance is 1K, this resistance is 5K. That means based on the analysis we did, the gain was equal to -5. Is that okay? With the approximation we made an approximation to make the analysis easy. Okay, I got -5. But I want to show you now here, if I use the exact model, it's really funny. I will find that the gain is equal to -4.9996. Look how small the error. Okay, I just complicated the circuit just to do anyway. So the purpose of this example here, just to tell you the ideal model we are using is actually easy to, it can make the calculation very easy, and it gives very good accuracy. So there is no need to use this model. Okay, what we call it practical model. Anyway, so let's see if I want to use the practical model, how I can do it. Okay, all I'm gonna do here is this model here is equivalent to the OM. So I'm gonna remove the OM and then I'm gonna put this model here. Okay, that's it. And then connect everything everything here. Okay, so this is the OM here. We have a resistance from here to here, RF. So I'm gonna put it here. We have a resistance this one. Okay, this one is connected to the ground, so I will connect this one to ground as you see here. Okay, V1 here is actually connected to RS and VS, RS and VS. Okay. So this is how the circuit looks like. So now after that, we are gonna do, I will do just, I'm gonna redraw it. Nothing is new here. I'm gonna just redraw it, okay? So this circuit is equivalent to this circuit, okay? Can you do analysis for this circuit? For sure you can, because this is what we have done so far. You have a circuit that has independent voltage source, just a number of resistors, and dependent source. Okay, can you do analysis? Yes, I can do it. The analysis I can do it using mesh or using the nodal approach, whatever approach you are using. Okay, so in chapter 4 I explained 3 approaches. Okay, you can use any one of them. So here I decided to use the mesh approach. I'm assuming I1 here and the I2 here, this way, okay? And then I'm gonna apply here Kirchhoff voltage law. This is how mesh works. So here I'm gonna apply Kirchhoff voltage law here, okay? If you apply Kirchhoff voltage law here, so this one, I1 times this resistance, RS times I1. The current in this branch is actually I1 minus I2 times RI, okay? And then here we have negative VS. So this is the first equation. I can get another equation here. In this equation, I2 times RF, okay, as you see here. Also, I have I2 times R out, as you see here. Also, I have here I2 minus R1, because this is a current here, I2 minus I1 times RR, okay? And then plus this resistance, plus this 10 to the power 5 VI, okay? AVI here. Okay, I have 2 equations, but the problem now, these 2 equations have three unknowns. It has I1, I2, and VI here, okay? So it's very simple. VI here, actually, the VI here is actually I1, the voltage drop here is actually I1 minus I2 times RI, or I2 minus R1 times RI, okay? Yeah, because I mix the direction this way. So here I2 minus I1 times VI, okay? So now I have two, I can replace VI by this, by this one here. By this way, I have only 2 unknowns, I1 and I2. Okay, so now I have 2 equations in 2 unknowns, I1 and I2. Okay, after you get I1 and I2, so you need to solve these 2 equations. After you solve them, I want to get V out here. I want to get V out here. Okay, so here V out should equal the V out you have here should equal I2, the voltage drop from here to here, which is I2 times R0 here, the voltage drop plus this voltage drop, as you see here. The voltage drop from here to here equals this voltage drop here plus the voltage drop here. For this voltage drop here, I need I2, only I2. So I2 times R0 plus AVI. Okay. After that, you can do the calculations. You can do the calculation you have here. And then after that, you will find V out should equal 4.999 VS. Okay. Any questions? Anyway, again, if this is too difficult, you don't need to worry about this example. I just want to give you this example. Yes, we are not using the practical model or the real model. We are using approximated model. We call it ideal OPN, but it's okay. It gives good results. So in order to convince you, I give you this example. But in exams, in quizzes, anything, well, I'm not gonna ask you to do that. I'm not gonna ask you to use this model at all. You understand what I'm saying? I just similar to what I explained in this chapter. You can all the time you can use the ideal model. That's should be okay. I'm not gonna ask this example. If just you can cancel it if you want, okay. But just this one, it's useful just to understand how the ideal model we are using and the assumption we need. Okay. So actually here in this circuit, the thing I didn't do here, but you can do when you go home, is actually you can calculate I1. Here you can calculate I1 and I2 and see what are the values for I1 and I2. Okay, we assume they are zeros. You will find they are not zeros, but very, very small. Okay, same thing, you can calculate what is the voltage drop here. What is the voltage drop? What is VR? Okay, the voltage drop we have here. Okay, so you will find this VI is actually is a very, 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 very small value. Okay, because and that's because that means our approximation is accurate, right? Because we assume the VI here is zero. We assume the voltage here and voltage here are equal. We assume that. We assume I1 and I2 are zeros. We assume that. Okay. Anyway, any questions? Okay. You know the test will be on Thursday. I sent you the exact topics you need to study. Okay, for the. Now I'm gonna move to chapter number 7. Okay. So let me tell you what we did so far in this course. What we did so far in the in the first lecture, I told you this course is about circuit, electrical circuit. And I told you what is electrical circuit? It's just a number of elements are connected together. If you have a number of elements, you connect them together, and you have to make close pair. Okay, this is a circuit. And then I started to teach these elements can be resistors, they can be voltage sources, and even voltage sources can be dependent and independent. Also, it can be current sources. Same thing, the current sources can be dependent or independent. These are the elements I explained so far. And then after that, also I explained op-amp. So op-amp is considered like an element in the circuit. That's in the last chapter. In chapter 6, I explained if you have an op-amp, in addition, if you have an op-amp in the circuit, in addition to these elements, how can you analyze it? In this chapter, in the coming chapter, I'm going to explain two more. I'm going to start to explain two more elements. Very popular. We use it almost everywhere. So one element here we call it capacitors and inductors. Okay. So I'm going to explain. How we make them. Okay. How they are made. Okay. More importantly, I'm going to explain what is the relation. Always we care about the relation between I and V. Okay. Remember, in a resistors, the relation between I and V. Okay. So here V equal I times R. Or Ohm's law. This is the relation. Okay. Here we're going to have different relation for this element between I and V. Okay. Also, remember, in voltage source, if you have a voltage source, always V is constant. V always constant. But the it changes based on the rest of the circuit. Okay. But also in case of current source, the current is always constant. Okay. But the voltage here, it changes based on the rest of the circuit. Okay. So always we are interested in the relation between V and R. So I'm going to start with capacitor. What are capacitors? What they are doing? How is it different from resistors? And what is the relation between V and I? Same thing for inductors and so on. That's what we accept. So let's see here. I'm making look at the title here. Energy storage elements. Energy storage, yes, because capacitor and inductors are actually store energy. This is completely different from resistors. Okay, resistors consume or absorb energy. So here, these two elements, the capacitor and inductors, actually they store energy, electrical energy under certain situation. Also, they release this energy at some situation. So you can see that they store energy and they release energy. Okay, this is completely different from resistors. Resistors all the time they consume or absorb energy all the time. Okay, so resistors all the time they consume energy. But these two elements here, sometimes they like if you have a capacitor, this capacitor can charge. When it charges, actually it's storing energy, or it can discharge. When it discharges, actually it is releasing energy, it's a stored energy. Same thing for inductor, as I'm gonna explain. Okay? Anyway, one more thing here, I want to make a definition, the difference between static circuits and dynamic circuits. Any circuit that contains these elements, inductor and the capacitor, I want to tell you, we still in the circuit we are going to use resistor, still we are going to use voltage sources, current sources, we still are going to use them, okay? But on top of that, we are going to see a capacitor and inductors, okay? If the circuit has only, it doesn't have any capacitor or inductor, we call it a static circuit. But anyway, just a definition. Let's start with the first one, capacitor. First of all, look at this picture. Maybe you're already familiar with these elements here. Maybe you have seen them somewhere. Okay. So all this picture for different types of capacitor. All of them are capacitor. Okay. So how these capacitors are made? How they are made? Okay, I'm gonna tell you how. Okay. Look here. As you see in this figure, one way to create capacitor by having plates, two plates. Okay, so for example, you can see this one as one plate. This is a second plate. You can put two plates this way, and there's a space between them. In this space, usually we put an insulator, okay, between them. That's it. So two plates, okay. The distance is as you see here, two plates in parallel. Okay, this is inside the element itself. Okay, it's how it is made, and we put between them we put an insulator. Okay. So here, as you see, we have two plates. The area of each plate, I'm gonna call it A. So the area here, this area is A, area A. The distance between them, this distance, okay, this distance, they don't touch each other, because if they touch each other, it's gonna make a short circuit. What I'm saying? So there is a separation between them. Okay. And the distance here is D. And between the two plates here, we put an insulator. We call it dielectric material or insulator. Okay. So what happens when you connect this plate to a voltage source this way and this plate to a voltage source? What happens? The charges are gonna move from here, and then this plate is gonna have some charges. The other one is gonna have negative charges. So this plate is connected to the negative side. This one has positive charges, negative charges, and between them there is electrical field. Okay, between these two charges. Okay, and this is how the energy is stored in the form of electric field. So, any question here? Just you have two plates. These plates are metal. These two plates are metal, and we put between them insulator. They should not touch each other, because if they touch each other, it's short circuit. Okay? And because you put insulator, current cannot go through from one plate to the other plate. It can't, because you put insulator. Current cannot go in insulator. Okay? Anyway, so here I'm going to explain something very important here related to capacitor. We'll call it capacitance. Okay? So capacitance is a parameter that can be used to measure its ability to store charges. Capacity, how much capacity do you have? You got what I'm saying? So the higher the capacity, that means it can store more charges, bigger space. You have big space. Got what I'm saying? Anyway, so here every capacitor has or parameter, we call it capacitance. These capacitance can tell how much energy can be stored, how much charges can be stored. Higher capacitance, that means it can store more charges, okay, more energy. Okay. So how can we calculate this capacitance and what this capacitance depends on? So this is the formula we are using. The capacitance equal to epsilon times A divided by D. So A and D, these are the dimensions of the dimension we have here. A is the area here, the area. D is the distance between them. So, okay. So here A is this area. D is the distance between them. Okay. And so these two are related to the dimensions of the capacitor. Also, we have another term here, epsilon, which is related to the material you put here, related to the material. Okay? So this capacitance this capacitance is constant. Once you have a certain capacitance, I can't change it. Okay, because it's related to the dimension. Unless you change the dimension, that's a different story. Okay, related to the dimension is related to what material you put here. Okay? But there is something we call it aging factor. Because of the age, maybe the material inside it may have different changes, and this may change the capacitance, the value a little bit, something like that, but that's a different issue. Anyway, so A is the cross-section area, this area here of this plane. D is the distance, the thickness of the distance here. Epsilon is related to the material you put here. So epsilon actually should equal to epsilon R times epsilon naught. Epsilon naught here is actually, this is the epsilon is called permittivity of the dielectric. Okay, so epsilon naught is actually equal constant value, and this is actually the permittivity of the free space for air. So here epsilon should equal epsilon naught, which this is the permittivity of the free space for air, times epsilon R. This epsilon R, we call it relative permittivity, and this one different from one material to another. This one different from one. So this one here, this is for the air. For this one is constant, but this one it depends on the material you are using. Okay. Okay. So you can see here, this capacitance is constant. Okay. Once it depends on the dimension, what material you are using here. But let's try to understand this formula here. So this formula is telling me, the bigger the area, the higher the capacitance. The bigger the area, so as you make the area bigger, okay, the plate can store more charges, higher the capacitance. Okay, this is number one. Number two, the smaller d, as so here, this is big D. So capacitance is a small capacitance. It cannot store much. But as they get closer to each other, now as you reduce D, actually capacitance increases. Okay? It can store more. Same thing here, the epsilon R, higher epsilon R, that means it's a bit larger capacitance. So this is related to the material. So if I want to get high capacitance, so I have to select a material that has a high epsilon R. Is that okay? So this is C, capacitance. It's a constant value because we're not going to change the dimensions. This is something, it's not related to the voltage, it's not related to the current, it's just related to the dimensions of the capacitor. Okay. So now I want to get relation between the voltage across the capacitor and the amount, the voltage and the charge, amount of charge stored by the capacitor. The relation, so this is the relation between voltage and the charge relation. You can see here, Q, which is the amount of charge, should equal to C times V, or V equal Q divided by C. C is the capacitance. Okay, So you can take here, what you can take here, for the same capacitance, as you increase the voltage, you can have more Q. Okay? And from this formula, I want to get the unit of the capacitance. So what unit we are using for the capacitance? So here actually the capacitance from this formula here. So again, this formula gives you the relation between voltage and Q. Q is the amount of charge stored here. Okay? And you can see here the capacitance equal to Q divided by V. V is volt, Q is coulomb, as we explained before, coulomb. Okay? So coulomb divided by volt, that's what we call farad. Farad. So this is the unit we are using for capacitance. And usually, as I'm going to explain, I have very interesting slide here. Farad, this farad is a very big number. 1 farad is something too big. That's why most of the capacitor, when you buy them, you will find the capacitor are in microfarad, nanofarad, picofarad, because 1 farad is too big. Okay. Voltage, 1 voltage is not that big. 1 voltage, right? But 1 ampere is also something big for especially for our small devices. Okay, that's why usually we use 1 milliampere, something like that. But 1 farad is a very big value. Okay, that's why all the capacitors usually we make them in microfarad, nanofarad, picofarad. Okay. So I have some numbers here just to convince you how big is 1 farad. Okay, assuming here, assuming I have a capacitor and the distance is just a very small distance, 1.01 multiplied by the 10 to the power of -4 meter. Okay, so it's like it's as thin as a piece of paper. So the distance between, so I made the distance very small distance. So are very close to each other. The distance is very small. Is that okay? And then I'm gonna put here air between them. I'm gonna put air. So to make 1 farad, how big should be the area? Okay, to have a capacitor with 1 farad, how big is the area? So if you do the calculation, you will find the area should be 4.4 miles square to make 1 farad in this. Okay, so I made the distance very small. Okay, and I put air between them. And to have 1 farad, so the size, the area has to be so big area. Okay. Anyway, I want to tell you usually the capacitor are using in micro, in nano, in pico. Okay. Micro is 10 to the power of -6. Nano is 10 to the power of -9, right? Pico 12. Can anyone tell me? Micro 10 to the power of -6. Okay. Nano 10 to the power of -9. Pico 10 to the power of -12. Anyway. So what symbol we are going to use for a capacitor? You are going to use this symbol or use this symbol. Okay. So this is the symbol, or this is the symbol we are going to use for a capacitor. So if you have, so here, for example, I'm going to put a capacitor this way, here in this circuit. Now, I want to get a relation. So I already have a relation between the voltage across the capacitor and the amount of charge. The relation is Q equals CV. Okay. Now, I want to get the relation between V and I. V and I. Okay. The voltage across the capacitor and the current. Okay. So the relation is, so I'm gonna drive this relation using the first one. So here Q equals CV. So if I calculate the derivative of both sides, dq by dt, which is I, okay. So you know from this course, dq by dt is I, okay, should equal. If C is constant, that's why I can get it out. I put it out, okay. So if you calculate the derivative of this part, because C is constant, I can get it out. So C dV by dt. Okay. And this is the relation here between I and V. Look at the relation. I equals C. C is constant. I'm repeating it. C is constant. That doesn't depend on current voltage, doesn't depend on anything. It's just a constant value. Okay. So I equals C dV divided by dt. Differentiation or the change in the voltage. The current equal to the change in the voltage across this area. So this formula is corresponding to Ohm's law in resistance. I equal VR. I equal VR, V equal IR gives you a relation between V and I in the resistor. But this formula here in case of a capacitors, this is the relation between I and V. Okay? So if you have V and you want to calculate I, you can use this one. What if I have V? What if I have I and I want to calculate V? Okay, so here I'm going to use calculus. In calculus, okay, so here I can, this one should equal to this one here, just okay, because I want to get V. You know, if you have here differentiation this way, I'm gonna make it integration to get V. The relation between V and I is integration. So I can make it this is from calculus. I can make it this way, and then after that I can integrate. So now actually, if you V is equal 1 over C integration from negative infinity to T I. So if you have, again, very simple. This is the relation between I and V. Okay? So if you have V and you want to get I, you can use this formula. Very simple. Okay? And this one is similar to this one. I just did some calculus manipulation, okay, and some algebra manipulation. So this one here is actually, I'm going to use this one. If you have I and I want to get V, I can do integration. So if you have I and you want to get V, you can do integration. Okay, for sure. We did something similar to this one in chapter 1, Q and I. If you have Q and I, okay, I equal differentiation of Q, or Q equals the integration of I. That's what we did. It was even the first quiz. It's almost the same thing, but this time it's between I and V. It's almost the same thing. So here I can split this limit here from negative infinity to T to make it from negative infinity to 0, or T naught. T naught here is the initial value, T0 to Tt. And then I can take this part here, okay, this part here, which is from negative infinity to 0, this will be the initial value, the initial voltage here, okay. So conclusion, the final conclusion, the relation between V and I can be calculated this way, okay. This is, if you have V and you want to get I, so you need to differentiate it this way to get I, okay. Or if you have I and you want to get V, you are going to use this one this way. Any questions? Yes.
So with the capacitor symbol in the symbolic form, is there a specific like direction where one side is always positive, one side is always negative, like from the symbol, we can tell that?
Yeah, that's a very good question. So here in analysis, okay, so there are two types of capacitors. One type of capacitors, I'm talking about practically, okay? But here they don't have we're not going to use polarity here, but practically, for example, this capacitor here, it does not have a polarity. That means any terminal can be plus or negative. It doesn't matter. You can flip it. It doesn't matter. Okay. However, if you look at this one here, this one has polarity. Polarity means there is one terminal has to be connected to the positive side, and one terminal has to be connected to the negative side. Otherwise, if you flip it, it's gonna pop. Okay, you are gonna damage it because there is some chemical. You are gonna do some chemical reaction inside it, and it's gonna. Okay, so you can see here. I'm not sure if I can. Yeah, you can see here. There is negative here. Same thing here. So it's you can same thing here if you look here, but it's not shown here. But usually the negative side, the right negative. You continue this negative side. Okay? So practically, yes, some resistors, it doesn't, sorry, some capacitor, it doesn't matter, the polarity doesn't matter, but for some of them, yes, it matters, and you have to be careful when you use it, okay? But here in analysis, I'm gonna use any symbol, it's not a big deal. Okay, so let's now come to the conclusion I have. This is the relation between I and V, okay? So if you have V, you can plug it in here to get the I, the current, okay? This is the current here, this is the current, and this is I. This is the voltage across the capacitor. Okay, I'm gonna repeat it again, guys. This current is not gonna come this way, right? Because there's inside here, there's insulator. It's not gonna go through it because there's insulator inside, right? So here as well, this is the relation. It's exactly the same thing like this one, but here this is given I. How can you get the voltage this way? Okay. This one is telling you something interesting. Okay, if you look at this one here. If the voltage here, if the voltage source is constant voltage source, so what should be the current using this equation here? If V is a constant voltage source, 0, yes, because the differentiation here is 0. Okay, so here, yes, if you have a constant, you know what do you mean by constant voltage source? That means if this is the time, since the voltage is going to give you constant voltage all the time, like batteries, the small batteries we're using, okay? But we have other sources that can have a change, okay? A change. This is DC voltage, this is AC voltage. So there's a change in the voltage, okay? So that means here, so here I should equal C dV by dt. So this should equal to 0, okay? So as I'm gonna explain in next chapter in details, actually what happens is, if you have a resistance here, and then you have a switch, and then you have a capacitor this way, and then you have a battery here, this battery, for example, 5 volt, what happens is, okay, once I close the switch, there should be some current in the very beginning. There is some current in the very beginning to charge the capacitor, okay? And this current will die. It's gonna die quickly. And this is what we call a transit period, just for a small time. Once this capacitor is charged by 5 volts, so after that, the current is equal to 0. There is no current after that. That's what we call a steady state. Steady state. I'm going to give you more details in next chapter. Let me say it again. Now, assuming the capacitor does not have any charge, once I close the switch, for a very short period of time, there will be a current just to put some charges here. This current this is how the current looks like. You start from high current, and then it's gonna die quickly. And this small time we call it transit. Okay. After this period of time, this capacitor becomes like open circuit. And now the current, now you can use this like I equals C dV by dt. Okay, and the current now equal to 0. There is no current. And because this one is open circuit, the voltage here, the voltage across the capacitor is equal to the same voltage like this one. It's going to be 5 volts. Like open circuit, you have open circuit. No current. So in the beginning, you have very little current in the very beginning to charge it. And then after that, there is no current. Once the voltage is equal to this voltage, again, this happens when the input is DC input. Okay, when the input is constant. Any questions? I don't want to be confused. So yes, still this one is true, but not in the transit, not in the very beginning, Okay, but yes, the current is going to become 0 because there is no change in V. But in the very beginning, there is some current to charge the capacitor. Any questions? So the next thing here, maybe I'm going to explain next time. So now I explained two main formulas. Q is the amount of charge on the plates equals C times V. Also I equals C, the capacitance, dV by dt, and this is the formula for V given I. What I'm gonna explain next time, how can we calculate the energy stored by the capacitor? Because again, you need to keep in mind the capacitor and inductors, they store energy. At some point they charge and then they discharge. So, okay, and in some situations the capacitor is gonna charge, and other situations it's gonna discharge. When it charges, actually, this means it is storing energy. When it discharges, that means it is releasing the energy. So it's completely different from what resistors are doing. So the capacitor and inductors all the time they store, release, store, release, store, release. Okay, energy. Okay, I think so. Next time I will explain how much energy is stored by the capacitor here. The final, I'm going to explain next time, but we'll get another formula, which is half capacitance V squared. This will give you the amount of energy stored by the capacitor. Okay, thanks.